Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And very good morning. This lecture is the third lecture of the series, and in this limited time, we will cover the general curvilinear motion, and in particular, the XY coordinates. So in this general curvilinear motion, there are three coordinates that of concern to us. The first is the XY coordinates. The second is the normal tangent, so-called NT, and the third one is the radius in theta r theta. So with that, we will be able to cover all the particles kinematics in this lecture. The first part is on the general curvilinear motion. What we mean by curvilinear motion is that assuming there is a path, it's a general path, and then what we need to know from this motion, let's say a particle is following the path, that's a particle, at time of t1 is here, and time of t2 is here, and time of t3 is here. Okay, and that's so it's moving from left to right. So the velocity of the particle is always tangent to the path. This is just the first point that I want for you to get across, that the velocity is always tangent to the path. So where is the tangent to this? So let's say this is the tangent. Okay, so that is the velocity. I'm going to underline V because it's a vector now. Okay, and at T2 there is a tangent to T2 at this particular curve. So let's say this is the tangential line. So that is the velocity of that particular point, and there's a tangent here. So that is also at V1. That particular these are the velocity. So velocity is always tangent to the path. It means that you cannot draw the velocity as this. Yeah. So this is wrong. Or you just want to, I feel like drawing this way. No, this is wrong. Yeah. So it's always tangent to the path. I hope you can remember that. So we'll start with the XY coordinate system, the Cartesian coordinate system. What is a Cartesian coordinate system? Basically, it's a two set of axes perpendicular to each other. One is the vertical axis, and we'll take that as the y-axis, and the other one is the x-axis. Okay, so that is basically the XY coordinate system. And if there is any point of position of a particle here, we have what we call as the position vector. Okay, and that position vector is represented by R underlined. So that is the position vector. Let me close it. This is the position vector. And position vector is represented by, so the coordinate of the system is now, let's say it is x and y. It's a scalar. The coordinate of the system is x and y, and the position vector is now represented by r, x, with a unit vector I, plus y, coordinate y, with a unit vector j. If we were to add another axis, which is the xy axis, then we have to use our right hand system. So now using the right hand system, so this is my thumb, this is my fingers, first finger, and then middle fingers. Okay, I hope you can understand this drawing. So it's not a beautiful drawing. Yeah. So this is x, y, and z axis. So we can also add the z component by x, y, z, and we have the unit vector k represented in the z axis. So the unit vector here is I, j for the y direction, and k for the z direction. So we will have the xy coordinates as xy, j and k. So that's your first system. So for example, we have a coordinate system of, let's say, so we can write the position vector as r equals to x I, unit vector in the x direction, yj, j is the unit vector in the y direction, and zk. So from that position vector, we can differentiate the position vector to obtain the velocity vector. So we can write the velocity vector v with the underline below to show it's a vector. Is the differentiation of the position vector dr over dt. So we can now start to differentiate the whole term xi plus yj plus zk. As these two terms are all in pairs, so we can now differentiate them one at a time. So we have the first for x, dx over dt I plus x di over dt plus dy over dt j plus y dj over dt, and then is the final term dz over dtk plus z dk over dt. So when you differentiate dx over dt, it becomes like x dot, assuming that x changes with time, x dot I, x di over dt, di over dt does not change with time, so we can cancel that. So this is does not change with time, it becomes 0. It goes the same to dj over dt, is 0, dk over dt. The unit vector does not change with time, nor does it change the direction or the magnitude with time. So dz over dk over dt is also 0. So we can simplify all our terms here as x dot I plus y dot j plus z dot k. Similarly, we will differentiate the velocity vector to get the acceleration vector a. This is a equals to dv over dt. We can now differentiate that in terms. So d over dt, kita gantikan, we substitute the velocity vector with x dot I plus y dot j plus z dot k. Okay, Similarly, we can repeat the whole exercise as before. We will get dx dot dt I plus dy dot dt j sorry, I'm gonna cancel this. I'm gonna simplify that. I'm going to use the same process here. So we have to rewrite something. Yeah. So here is we can get dx dot dt I plus x di over dt plus dy dot dt j is a dot plus y dot dj over dt. So that's the term for x and the term for y. And can you complete that term for z? Yeah. And because this is 0, di over dt is 0, similarly dj over dt is 0, similarly also here, so we will have the acceleration vector a as d x double dot nampak double dot dt I plus dy double dot, sorry, d, so it becomes, oh, my mistake again. Here is, I'm gonna rub this out. So this there is no dot here. Dx dot dt, so dx dt x dot. Okay, I have to represent this now with a term of vx I, and then this is vy j and vz. Okay, so it's the matching is like x dot equals to vx, and then for the green one, y dot equals to vy, and then for the blue one, z dot equals to vz. Okay, so we get that acceleration as dv or dvx, coming back to here. So we have that dvx over dti plus dvy over dtj, unit vector j, that is the direction, and then finally we have dvk over the dvz. So vz, this is unit vector k. So that is the expression for the acceleration, and this is the expression for the velocity. So the velocity vector here, v equals to k, or these three expressions. So this one we can rewrite a as axi, unit vector, and ayj, and this is az. Okay, so unit vector is So that is the expression for acceleration. Okay. So individually we can say that ax equals to dvx over t, and ay equals to dvy over dt, and az equals to dvz over dt. So I think it's quite straightforward for you to follow that kind of arguments. Yeah. So this is an example 3.1 where position of a particle is given at x equals to 8t m and y equals to x squared. This is x squared, not x2 over 10 m, where t is in seconds. Determine the velocity and acceleration vector at t equals to 2 seconds and the magnitude of each, i.e. the velocity and acceleration. So we have got the first equation, which is like x equals to 8t. Let's put that as the first equation. And then we got the second equation, y equals to x squared over 10. So we are usually going to go for the derivative of this equation. So why not we just find the derivative of each. So the first derivative of x equals to, so vx equals to dx over dt, and that gives us 8. And then ax equals to vx dvx over dt, and then that gives us 0 because vx is constant, so that's 8 meters per second. And then we have y, and we don't have a y is not given as a function of t, but y is given a function of x. So let's find dy dx equals to 2x over 10, and d2y over dx squared is equals to 2. Yeah, so these are the sets of equations that we have. So let's see, we need to find the velocity and acceleration at t equals to 2 seconds. So the v at t equals to 2 seconds is equals to, we know what vx is. We know what vx is. Vx is 8. We need to find vy. So we know what vx is. Vx equals to 8. But vy equals to dy over dt. That is not known, but we have a dy over dx times dx over dt. And therefore, we can write here vy equals to dy over dx is 2x over 10, and dx over dt is to 8. Okay, so at t equals to, so we know that at t equals to 2 seconds, at t equals to 2 seconds, vx equals to 8. So we just substitute this value. Yeah, so 2 times 8 over 10, okay, times 8. So we got 64 times 2, 128 over 10. So vy equals to 128 over 10 equals to 12.8 meter per second. So what is the magnitude of acceleration? So the magnitude is v equals to vx squared plus vy squared, and you can put in those values. Yeah, so those values of vx, so I can put in the values. Vx 8 square plus 12.8 square. Yeah, so whole x squared 2x and 2x dy over dx is 2x over 10, 2 kali 16, x equals, sorry, we made a mistake here because at t equals to 2, dy over x is t to x equals to 8 times 2 equals to 16. Can you see where my mistake is? So this is 2 times 16, so I will now remove that x. This x is now 16. Padam dulu lah semua. So 2 times 16 times 8, 216, 8 over 10. So this is 25.6. So it's 256. So it's 25.6 meter per second, and therefore my Vy here is 25.6 square. Yeah, so we've got our magnitude at 26.8. That will be our answer for the first question. Now we want to find the acceleration at that particular time. So ax, so we have to find the acceleration now. So the acceleration ax equals to dvx over dt, and vx over dt is already 0, we know that. Now we want to find ay. Ay, we have dvy over dvy over dt. Yeah, so we know that vy is 2x, and then is 2x x dot 2x dy over dy over dx is 2x over 10, and then x dot, okay, equals to d over dt, all this expression. So we will get ay equals to 2x dot over 10, okay, plus 2x x double dot. This is the chain rule. Let me make double dot clear, double dot over 10, and substitute. So at t equals to 2, x equals 16, and x dot equals to 8. Okay, so x dot equals, so kita akan dapati, so we will have ay2 h square over 10 plus 2 16 x double dot is 0 to 16 0 over 10, and we will have y equals to 12.8 meter per second square. So that's from there you can find the magnitude. So if you want to find the magnitude, let me clear the space here. Let me clear the space here. So the magnitude of A, so A equals to, the magnitude of A is ax square plus ay square. And you know what your ax is? Ax is 0. Yeah. So ax is 0 square plus 12.8 square. So the magnitude is 12.8 meter. This is the magnitude. So you find the vector ax, ay. It's just a matter of adding the unit vector. You can do that on your own. Yeah. So the next one. So we go to the next one, which is the motion of a projectile. A projectile is a special case of application of the xy coordinate system. So you have an xy coordinate system. Yeah. So this is x and this is y, and you can launch a projectile at a certain angle. So let's say this is your velocity. So you can launch your certain angle, and you got the magnitude of the vector velocity there, and usually you will know what the angle is. Yeah. So when the projectile leaves the gun, its acceleration in the x-axis, okay, is 0, and the y-axis acceleration is g equals to 9.8 meter per second square. So this is what we assume, that when the projectile is traveling, it has a velocity v, and it has a acceleration due to the gravity. So that is I'll use a double arrow here to indicate that g is always directed downwards, and we can take it as 9.8 meter per second square. Okay, so that is the case. So when a projectile is traveling, the key issue is to find the how far it travels. Okay, so that is called the range. And how long it travels. So time of travel. So that's how long does it take to move from the origin to the place where it landed. So we can make some calculations there. Okay. So what is the assumption here? We know that the velocity, there are two components of velocity here. So there is the Vy and this Vx. Okay, so at t equals to 0, the projectile is launched. So we know that Vx is a certain number, and we have a Vy, and from there the velocity of Vx over time, and also Ax, there is no acceleration in the x direction, and there is acceleration in the y direction, which is equals to minus g, and that's equals to 9 minus 9.81 meter per second square. This is downwards, yeah. So what we have here is that we can calculate the final, because Vx doesn't change with time, so it's constant, so we need to find after a t, so at maximum height and at landing. These are two issues that we want to know. So from Vx, we know that the x equals to the integration of Vx with dt from 0 to t. So we know that the range equals to x. This is x. So that's equals to Vxt. And we also know that y equals to Vy minus gt, because of the acceleration, constant acceleration. This is constant acceleration. I need to remind this is a constant acceleration. Sorry, this is Vy. So this is Vy naught. So that we can find that y equals to integration of Vy dt, integration of Vy naught minus gt dt. So we will have, from, if it's from 0 to y, assuming that it's from the 0 elevation, yeah, so it becomes Vy naught t minus half gt square. So that is the equation for the distance traveled in y and the distance traveled in x and y. So from there, so let me clear some space here. Let me clear some space so that I can use this for my calculation. So at maximum height, what happened at maximum height? Vy becomes 0. It has to stop, so that we have a condition where y naught t equals or minus this is Vy naught t minus half gt squared is equals to 0. Then we can find that Vy naught t equals to half gt squared. So what we have is time. Times equals to 2 Vy naught over g. So that, my dear, is the time need to reach the maximum height. So time of flight. So the time of flight becomes time of flight is 2t, because it has to move up satu and then come back down the same time, using the same magnitude of time, same length of time. So we have time of flight is 4 Vy naught over g. So that is the equation of time of flight. right? Do we need to remember that? I don't think so. We have to really remember that, but that's how we go about that. So let's see how we use this equation to solve one particular example. So I will calculate the time of travel and the distance based on this assumption. So let's see one example. Here is a case where a particle slides off a ramp. So there is a ramp. This is a ramp, and there's a particle that slides. Okay. And it leaves at a horizontal velocity at 12 meters per second. And the height of the ramp is from this to the ground is 6 meters. So this thing will start to fall, and you can have it stacked here. So they want to ask you what is the range here. Find the range and the time needed for the sack to hit the floor. So they also want to know what is the time needed, time of flight. So the range, so we have two sets of equation. We know that R equals to V x naught t. That's the first set of equation. And we know that the time to fly is that we know that y is the distance travel equals to Vy equals to Vy naught minus gt. Okay, this is the initial velocity, and from there we can integrate. So y is integration of Vy dt 0 to t, so is a Vy naught minus gt integrate dt, and we have Vy naught t minus dt square over 2, and let's call this the third equation. So here is a case where we know that y equals to 6 meters. So from equation 3, we can get t, yeah? So we will get from equation 3, so Vy naught is also 0 because there's no vertical component to the particle when it leaves the ramp. So we have the case where from equation 3, so we can rewrite the equation 3 is 6 equals to 0 t minus 9.81 t square over 2. So you will have t equals to minus 6. Y equals to minus 6. Why is it y equals to minus 6? Our datum is here, xy, so it's minus 6 below. So t equals to 2 times 6 divided by 9.81. Yeah, so you will have 1.11 second. That is the answer for number 1, the time needed, and then the distance traveled is straightforward from equation 1. From 1 we can have R equals to V naught t, Vx naught t, so that is 12 times 1.11, we'll have 13.3. That's this answers for requirement how far R is 13.3 meters. That's clear number. A simple example number. And the final example is where you have a particle released at 1 meter above the ground. So it's been released at 1 meter above ground. And at a slope of 30 degrees. So it is fired at 30 degrees with the speed of v. Determine the speed of release and the horizontals of travel. So it's asking you the same thing. What is the range R? And then maximum height attained, Y max. Okay, but what it gives us is the time of travel. So the time of flight from this point, let's say this point A to B, you can get the information from here. It gives you 1.5 seconds. So that is the information. Time of flight, TOF is 1.5 seconds. So I can take this data and I use it in several ways, but let us see how we can do this in a more systematic way. So we know that we are beginning not from zero but from a condition where it is 1 meter above the ground. So we start from point A, which is above point ground. We are going to use the time of flight data. This is the only data that we have. So the vertical component of the velocity, so Vy equals to V sine 30 degrees. Okay, and the Y max is the time of flight is up it goes to the Y max, and then down it goes to plus or minus 1. So the time of flight is let's see, Vy equals to V sine 30. So Y, and then Vy equals to V sine 30. This is Vy naught, yeah? Initial velocity. So that we know that Vy equals to Vy naught minus GT. Okay, so that the height obtained is, let's say the height obtained is Y. The height obtained is Y, and that is equals to Vy dt. Yeah, so I have to put, it is not from zero. Usually we put 0 here and we put Y, but currently we are not moving from 0. So this is the first flight, so 0 to Y, or 0 to, so at Y max it will become H. So anyway, we'll put this first as, so it's Vy naught minus GT, so dt, so we got Vy naught t minus GT squared over 2. So that's the first the so-called, so at max on the way down, this is on the way up, yeah. So on the way up, So on the way down, it's like so down. Let's say this is point like A. This is A0. This is A1, and this is A2. So this is from A0 to A1. From A1 to A2, when it starts to fall down, the distance travel is y minus 1, because it's going down. So it's y plus 1 equals to the same kind of travel now. So v naught t minus gt square over 2. So here is a case that we need to reconsider. So I'm going to remove this. So we have the equation here. I'm going to erase all this term to put it in perspective. So what we have is a time of flight from A to B, which is 1.5 seconds. Yeah. So that is. So we can now rewrite the equation of yb equals to yb travel from b distance travel in the yb equals to ya plus the equation in vy of t. So vy t, so vy naught t minus gt square over 2. So this is the set of equation that when you have some. So in this case, yb equals to minus 1, ya equals to 0, and this is happen when t equals to 1.5 given. This is a time of flight. So when you rewrite that equation, you have minus 1 equals to 0 plus vy. So that is va sine theta, or v sine 30, time of flight 1.5 minus 9.81, 1.5 square over 2. Yeah, so by that you know that the initial launch velocity is equals to 13.38 meter per second. So that's the launch velocity. So that's the speed of release. The horizontal travel. The horizontal travel is equals to r equals to sa or xa plus vx initial kali t, and this is 0, this is 0. So and then we have got 0 plus vx. Do you know what vx is? Is v cos 30. So it's v cos 30, and then t is known as 1.5. What is v? We know the value of v here. So you pump in the value of v. So we will have 13.38 cos 30 degrees times 1.5. So r equals to 17.4 meter. So that is the answer to the example number 3. So I hope you have some idea on how to use projectiles, whatever. So there are many examples in the book, or you can go to any other website. There are plenty of examples on projectile. But the biggest assumption is that there is no acceleration in the x direction, and the acceleration in y is constant because of gravity. Thank you very much. I'll see you in the next lecture.